Hello. Today we're gonna talk about exploring a bit Docker container security. Um, and let's just introduce a bit of ourselves first. So I'm Monica, and I've been a software developer at Thoughtworks for the last couple of years. And before that, I used to be a telecommunication engineer. And I'm very excited to be here today.
Hi, so I'm Marina, and I've been with Thoughtworks for just over a year, and I'm also a career changer, and I hope you'll enjoy the talk we prepared for you today.
So by now you've been asking yourself, what innovative thing about container security are Marina and Monica going to tell me about? Well, we're sorry to disappoint. There's nothing new or innovative here, and probably some of you already know what we're going to share today. But that's not the objective of our talk. What we wanted to show was that without having to be a specialist, because nor Marina or myself are in this topic, anyone can and should take a few things into account when it comes to working with Docker containers. So we know software containers have become more popular in recent years, as many organizations have discovered the benefits of containerization. Unfortunately, and as is often the case with the rapid advance in technologies, container security has been a bit neglected and is often an afterthought. So in this talk, we wanted to bring to light some of the main areas of concerns that are associated with using containers and some practices to keep in mind to avoid falling into these traps. We choose to focus our talk on Docker because it is a widely used technology and often can be synonymous with containerization. But we're by no means saying that this is the only option out there. And we would like to point out, however, that security is a huge topic. So there's no way we could fit everything in, nor we will try to. And while this talk doesn't intend to be an exhaustive guide to Docker security, for that you should always refer to the official Docker documentation. We wanted to share some good practices that we have learned along the way, and we think might help you as well. So before Docker, most organizations use virtual machines or bare metal servers to host applications. From a security perspective, these technologies are relatively simple. You need to focus on just two layers, the host environment and the application, when hardening your deployment and monitoring for security relevant events. You also typically don't worry that much about APIs, overlay networks, or complex software-defined storage configurations, because these are not usually a major part of virtual machine or bare metal deployments. So when talking about challenges of Docker container security being more complicated, it is largely because a typical Docker environment has many moving parts, which means you have more layers to secure. And those parts can include your containers, of course. You probably have multiple Docker container images, each hosting individual microservices. You probably also have multiple instances of each image running at a given time. Each of those images and instances needs to be secure and monitorable separately. The Docker daemon, which needs to be secure to keep the containers it hosts safe, and the host server, which could be bare metal or a virtual machine. And probably you host your containers in the cloud using a service like Elastic Container Service, and that is yet another layer to secure. And if there wasn't enough within Docker itself, you also have to worry about the overlay networks and APIs that facilitate communication between containers. And of course, any data volume or other storage system that exists externally from your containers. We know all of this can be overwhelming at first, and we wouldn't know where to start either. But next, Marina will help us take a closer look at some of the areas we should be concerned about when securing Docker containers so we can have a better understanding.
Thanks, Monica. So let's talk about the container lifecycle. So the process of securing your containers is something that should be continuous, and it should be integrated into your development process and automated so that you can remove the number of manual touch points. And then it should also be extended into the maintenance and the operation of all the underlying infrastructure. So this means you want to be protecting your build pipeline, your container images and runtime host, your platform, and also all the application layers. So implementing security as part of a continuous delivery lifecycle means that you will be mitigating risks and you'll be reducing vulnerabilities across what we would call an ever-growing attack surface. We're now going to go through each stage of the lifecycle to see which improvements you might be able to make. So one of the important parts of the build stage is that you want to be making sure that you're hardening your image. And a good way to get started with that is to use a linter for your Docker file. So this is a really useful tool because you can avoid making common mistakes, and you'll also be following best practice guidelines in an automated way. So that way you don't have to know them all off by heart. And we're actually going to point some of these out to you later in the talk. As for the actual linter, there's several places that you can put it. So you can add it in as part of your pipeline, and we're going to show you that in the demo later. And another option is to put it into your pre-commit hook. But ideally, you do want to be catching these mistakes even earlier on. So having a linter integrated into your IDE is actually probably the best option. However, depending on the tool that you choose, they might not always offer this. So it depends what suits you and your team best. So for security, for the Docker image security scanning, this is a process where you will be finding security vulnerabilities within the Docker image files. So typically these image scanners, they work by passing through the packages and other dependencies that are defined inside the container image file. And then they'll be checking to see whether there's any known vulnerabilities in those packages or dependencies. And while the security scanning is one of the critical ways to find flaws that could lead to a breach, then it is important to note that security scanning is by no means going to provide a full coverage for you, or full security coverage, because there are several potential security problems that image scanning won't help you find. So firstly, it won't check for security problems in your container environment. For example, running your image as root, which we'll cover later. Scanning's also not going to check for insecure shared resources between the containers, such as storage volumes or networking, because they exist outside of the container image. And it's also not going to find any unknown security vulnerabilities, because most of the scanning tools are checking against public vulnerability databases. And that's going to determine whether the package has a security problem or not. So if there is a security flaw that hasn't been publicly disclosed, then the scanner's not going to be able to find it. And vulnerabilities that aren't evident from a package name, so if you change the package name, then it won't be able to find any packages that aren't publicly monitored for security vulnerabilities. So as you can see, it is something that is going to have to be part of your container security strategy, and it is a crucial one. And it's also the primary means of defense against security flaws or insecure code within your container images. And for us, it's a foundational part of overall Docker security, despite all the things that it doesn't cover. So next, we're going to look at multi-stage builds. And while you're building your application with the Docker file, many of the artifacts that are created are required only during build time. So these can be packages that are for development tooling, or libraries that are required for compiling, or maybe dependencies that are required for running tests, or temporary files, or keeping secrets, and so on. So keeping all of these artifacts in the base image, which might be used for production, will actually result in an increased Docker image size. So this can actually badly affect the time spent downloading it, as well as increase the attack surface because more packages are installed. So the same is actually true for Docker image you're using. So you might need a specific Docker image for building, but you're not going to need it for the running of your application. So this is a good reason why Docker has the multi-stage build capability. So this feature allows you to use multiple temporary images in the build process, and then you'll only keep the latest image along with the information you copied onto it. And that way you'll have two images. So you'll have the first image, which is going to be really big in size because it's going to be bundled with all of the dependencies that are being used in order to build your app and to run all the tests and do all of that. And then you'll have the second image, which is a really thin one. And it's only going to have a copy of all the artifacts that were required to run the app in production. which brings us to our next topic, actually. So thinking about the size of your image, we also want to be thinking about where we're getting our images from. So usually when you start a project, you'll probably start your Docker file with the from keyword, and that's where you're going to get your base image from. And it's important to get these from trusted sources. And there's some really, really basic indicators, which you can see on the slides, which can help guide you when you're choosing one. So we've used Docker Hub as an example, and it is a good bet that popular official images are relatively safe. So they'll have the official image stamp, and they'll often have millions of downloads. Some other good indicators are that the image is Docker certified or that the publisher is verified. And even taking it a step further, you can also check that the updates are being made regularly. So here we have 1 hour ago, which is maybe a bit optimistic, but it is important to double check that the images if they haven't been updated in many years or something, it could mean that there's some vulnerabilities lying around. But then again, it could also just mean that the changes haven't been made because it's a stable one. So it is worth checking out. And related to using the official base image, you should also be trying to use a minimal base image. So with less code inside, there's going to be a lower chance for security vulnerabilities. So a smaller, less complicated base image is more transparent. So when you're specifying the image, you should take into consideration that the underlying image could potentially be a full-blown operating system. And if your project doesn't need things like system libraries or system utilities, then it's probably better to avoid using a full-blown operating system as a base image. And now looking at it from a security perspective, well, always a security perspective, but ideally you're going to be wanting a base image that's like starting from scratch, so a completely empty container. But that's not very practical, and it's not practical to build our own base images from nothing, because it might actually end up bringing more security issues in, considering that most of us probably aren't security experts. So the second best choice, in our opinion, is using Distroless, which is a set of lightweight images which are made by Google, and they were created with the intent to be secure. So these images contain the bare minimum that's needed for your app, and meaning that there's no shells, no package managers, or any other tools that would bloat the image or create any signal noise for security scanners, which would make it harder to establish compliance. So also, when you're looking to pull your images from online, they can have multiple tags, and often people will use the tag latest. But image tags, they're not immutable, which means that the author can publish the same tag multiple times. And that means that your base image might be changing in between builds, and that could lead to inconsistent behavior. So not only that, but with the changes, you could actually inject malicious code, and that's something that you won't have explicitly protected yourself against. So there are some ways to mitigate this. It is preferred if you use a more specific tag. So if the image has multiple tags such as 8 or 8.0.1 or even 8.0.1-Alpine, you would ideally be using the latter because it's the most specific image reference. So, but something that you do have to keep in mind if you are pinning a specific tag is that it might be deleted eventually. So to mitigate that issue, then you should consider maybe running a local mirror of this image in a registry or an account that's under your own control. So it's important to take into account that the maintenance overhead required for this approach, because it does mean you need to maintain your own registry. But replicating the image that you want in a registry that's owned by you is a good practice, and it's just going to make sure that nothing changes in the image. So it does seem like a bit of extra work, but it is worth it to avoid the potential of malicious code being injected without your knowledge, just because you're blindly pulling from latest and hoping for the best. And another thing you want to look out for is the authenticity of Docker images. So we do actually put a lot of trust into these images as we're literally using them as the container that runs our code in production. And that's why it is critical to make sure the image that we pull is the one that was published by the publisher, so that nobody else has modified it along the way. And tampering can actually occur in different ways. So it can happen between the Docker client and the registry, or by compromising the registry of the owner's account to push malicious images into it. So a way to verify that there hasn't been any tampering in between what you've pulled and what the image the owner originally created is to use something called Docker Content Trust, which we're going to explain in the next stages. And now I'm going to pass you over to Monica, who's going to take you through the next stages of the container lifecycle.
Thanks, Marina. So yeah, now let's see what can we do while we ship our images. So when transferring data among networked system, trust is a central concern. In particular, when communicating over an untrusted medium such as the internet. It is critical to ensure the integrity and the publisher of all the data a system operates on. For that, Docker Content Trust provides the ability to use digital signatures for data sent to and received from remote Docker registries. Publishers could be individuals or organizations manually signing their content, or even you can have automated software supply chains signing content as part of their release process. When it comes to shipping the image, we want it to be reliable. So signing your images is especially beneficial for your company if you have a private registry. And if you want to make sure only certain people can modify and push image tags, and as well helps prevent the users of these images from working with tag images unless they contain a signature or comes from a trusted source. So when we talk about resources by default, a container has no resource constraint and can use as much of a given resource as the host kernel schedule allows. So Docker provides a way to control how much memory or CPU a container can use, and the way to do this is to configure resource quotas on a per container basis. Without a resource limit, a container can use up all available memory. If that happens, the host kernel will kill kernel processes to free up memory, and any process is subject to killing, including Docker or any other important applications. This can effectively bring the entire system down if the wrong process is killed. So Docker attempts to mitigate this risk by adjusting the out-of-memory priority on the Docker daemon so that it's less likely to be killed than other processes on the system. The out-of-memory priority on containers is not adjusted, and this makes it more likely for an individual container to be killed than for the Docker daemon or other system process to be killed. So you should not try anyways to circumvent this safeguard by manually setting this adjustment to a string negative number on the daemon or on a container, or by setting the out-of-memory kill disable flag on a container. So, but some of the things that you can do to mitigate the risk of system instability due to out-of-memory are performing tests to understand the memory requirement of your application before placing it into production. Ensure that your application runs only on hosts with adequate resources, and limit the amount of memory your container can use. So setting resource quota is useful for several reasons. It can help you to keep your Docker environment efficient and prevent one container or application from hogging system resources. But it also enhances security by preventing a compromised container from consuming a large amount of resources in order to disrupt service or perform malicious activities. But it wouldn't be enough to set resource quota if we don't restrict a container's access to system resources. In order to have control on who can set these resources, Docker has a cluster management solution, the Universal Control Plane, that helps you manage your Docker cluster and applications through a single interface. And there's a specific feature designed to regulate user access to resources. So the process involves organizing your users into team based on their function. So you can easily assign no access beyond restricted or full permissions. So now that we know some of the things that we need to take care while building and shipping, let's see what can we do in runtime. When you run a container, Docker creates a set of namespaces and control groups for that container. These provide a layer of isolation. Each aspect of a container runs in a separate namespace, and its access is limited to only that one. The best way to prevent privilege escalation attacks from within a container is to configure your container's application to run as unprivileged users. For containers whose processes must run as the root user within the container, then you can always remap this user to a less privileged user on the Docker host. The map user can still function within the namespace as normal, but will have no privilege on the host machine itself. And as for control groups, they're yet another key component of containers. So they implement resource counting and limiting. So what they do not play a role in preventing on one container from accessing or affecting the data and processes of another container, they're essential to fend off some denial of service attacks. They're particularly important on multi-tenant platforms. Some of the things that control groups allows you to do are limiting resources. So groups can be set to not exceed a configured memory limit, which also includes the file system cache. Prioritization. So some groups may get a larger CPU share of a CPU utilization or disk throughput. And accounting help you measures how much of the resources certain systems use, so can help you detect anomalies if the systems start misbehaving. And finally, control the processes. So checkpointing, freezing, and restarting groups of processes can help you with this as well. And if you want to go a step further, you could use rootless mode. So rootless mode allows you to run the Docker daemon and containers as a no-root user to mitigate potential vulnerabilities in the daemon and in the container runtime. But how does this work? So rootless mode executes the Docker daemon and containers is in a user namespace. And this is very similar to what we've seen before, except that with user namespace remap mode, the daemon itself is running with root privileges. Whereas in rootless mode, both the daemon and the container are running without root privileges. And finally, Docker containers typically rely heavily on APIs and networks to communicate with each other. That's why it's important to make sure that your APIs and network architectures are designed securely, and that you monitor for anomalies that could indicate an intrusion. Since they're not part of Docker itself, but are instead resources that you use in conjunction with Docker, steps for securing these are beyond the scope of this talk. Nonetheless, they shouldn't be neglected. So now Marina is going to share with us a small demo we have prepared for you.
Cool, thanks. So you might feel like we've just bombarded you with a ton of information. Some of it you might have already known, and some are hopefully new insights that you can use from now on. We wanted to finish the talk with a small, simple demo where we're going to show you two different ways of scanning your images, and both of them can be part of your pipeline. So for the first one, you won't need anything apart from a valid token. And then for the second one, you'll have to install a plugin in Jenkins. So depending on what your needs are, you can choose which option's best for you. So for this demo, we'll be using the tools you can see here on the slides. So Docker is our container, of course, Jenkins for our pipeline, and Aqua microscanner for the image vulnerability scanning, and Hadolint for the Docker file linter. So we've chosen these tools for the sake of simplicity. They're by no means the only ones that are out there. Our aim is just to demonstrate how simple it can be to add image scanning to your CI/CD workflow by integrating it into your pipeline. So as an overview, we have set up a basic Dockerized app, which gets built in our Jenkins pipeline. We're building our image from a base image that we found on Docker Hub. And since we've already covered what to look out for when you're pulling images from a public registry, you already know that you should be looking for official images and using a tag that's currently being supported. And we've already done that previously, so we're not going to show it as part of the demo, but we'll explain the parts. So we're going to walk you through 3 commits that we did. So we prepared them earlier so you don't have to be bored watching pipelines run, because I'm sure you do that anyway, often enough. So for the first commit, we're going to make some more obvious mistakes so we can see how the tools can help catch the mistakes that we want to see. So we want to be seeing the scan failing. And we'll start by looking in the Docker file. So as you can see, it's pretty simple. We're doing some things that we want the linter to pick up. So we're building from Postgres latest, and we're not using a very specific tag, which we mentioned you should be doing. And the next thing is having the user as root. So Monica covered this earlier, outlining the risks of why your final container shouldn't be running as root. And then the other thing we wanted the linter to pick up is on line 3. So it is actually a good practice to use copy instead of add. So to explain this a little bit more, Docker provides 2 commands for copying the files from the host to the Docker image when building it. So those commands are copy and add. Copy lets you copy all the files recursively, given an explicit source and destination. So with copy, you're declaring both of the locations. Whereas with add, it's implicitly creating the destination if it's not existing. So that means it can accept local or remote URLs as its source, and they're going to expand or download into the destination directory. So try to use copy when you can, because it is more restrictive. And this is actually also advised by the Docker documentation. And the only reason that add exists is for backwards compatibility. So try to always use copy when possible. So the next section in the Docker file, you can see, is the first implementation of adding a vulnerability scanner. We've added it as a multi-stage block, which we also covered earlier. And the only thing that we need to make it work is a token. We're not going to go through the exact details of setting it up because it will vary between which tool you're using, and it's not really important for the demo. So next we can take a look at the Jenkins file. And so to start with, we have these stages. First, we'll run the linter, and then we'll verify whether the base image has been signed. And then we'll check, we'll build our app, and then finally we'll build our image and scan it. Yes. So now let's imagine that we've committed and pushed and the pipeline runs, and now we're going to go and have a look at the output. So you can see the pipeline's failed. And if we check the output for the linter, we can see that it's telling us what we should do to improve the Docker file, which is exactly the things that we were expecting. So we shouldn't be using the latest tag, we've set the user to root, and we're using add instead of copy. So they're all outlined there and picked up for us, which is great. So then we can go and have a look at the next stage, which is the signatures. So this image does have signatures. And if we wanted to, we could add in a condition to make sure that the image is coming from the owner and that it hasn't been tampered with along between the pool. So lastly, we can see that the build failed, and that was at the scanning stage. So we'll focus on the details of that in the next build. So now we're going to go through and clean things up. So let's go to our second commit. And we started by making changes in our file to please the linter. So what we've done in the Docker file is we've now used a little bit of a more specific tag, Postgres 13 instead of latest. And we've also added a specific group and user for this image. And finally, we replaced add with copy. So now that we've changed the things that the linter was telling us to improve, you might also notice that we've removed the multi-stage block where we had the scanner. So now is where we're going to show you the second approach, which is adding the scanner directly into your pipeline. So let's take a look at the new stages that we have in our Jenkins file. We've added the building of the image as a stage using the Docker plugin from Jenkins. And then we'll use the same scanning tool we had in our Docker file before, but this time we're going to have it installed as a plugin from Jenkins. So now we just have to specify our image name, and that's it. So that's the second approach to adding the scanning to your pipelines. And now we're going to pretend again that we've committed, pushed, and watched the pipeline run, and we'll check the output. So first, let's take a quick little peek into the linter so that we can see that now it doesn't have any new messages for us, so that's great. And we can also see that the scan is still failing. So now let's try and understand why it's failing. So we can look at what the results of the scan is, and we can see that it's saying that the image is non-compliant. And that's because it has at least one high severity vulnerability. So in this tab, we can see all the vulnerabilities that the scanner has found, and it shows you each individual CVE link. And the CVEs are common vulnerabilities and exposures, and they're a list of standardized names for security vulnerabilities. So these are the publicly disclosed vulnerabilities, which are stored in a big database, and most security scanners are going to check against that database to see if there's any present. And finally, if we have any sensitive data or malware, then you can see it in the other 2 tabs up there. So this is a much nicer output than the original one, which was just all clean, just text. So now what we want to do is get the pipeline passing. So for our third and last commit, we'll keep everything the same apart from our base image. So what we're going to do is we're going to change to a more secure base image, which hopefully won't have any high severity vulnerabilities. And that's it. We haven't made any other changes in the Docker file. So taking a look into our Jenkins file, you'll also see that the last stage is to deploy the image. So if the image scan passes, then the image is allowed and we'll be able to deploy it to a public registry. So those are the changes that have been made, and we're going to push again and have a look at the results. So we can go to the linter in case it picked anything up that was new, but it hasn't, so that's great. And if we go to the scan, we can see that it passes, yay! And it says that the image is allowed. And we can also see that there's no vulnerabilities at all. So I'm sure you're wondering, can I always find an image with everything that I need that has no vulnerabilities? And honestly, probably not. You might not always find a completely clean image, and that's okay. It's not terrible if you have some low or negligible vulnerabilities, but you definitely want to be checking out the high ones and probably also the medium ones and making sure that it's an okay thing to have. So as we said in this talk, like the recommendation is to choose an image and get a version that has the bare minimum that you need for the app and has the lowest amount of vulnerabilities. So lastly, we can see that in the pipeline, again, we can see that the image has been successfully deployed, and we can also see it in the registry. So there it is. And that is it for the demo. So I hope you can now see just how simple and quick it can be to add scanning to your pipeline, and that you do have various approaches to do so. So adding security scanning is the minimum that you can do when it comes to thinking about security in Docker. And as we mentioned before, it is the primary means of defense against security flaws or insecure code within a container image. So that's why we say that it really is a foundational part of overall Docker security, but it shouldn't be your only one.
And as you see, there are no simple tricks to maintain Docker container security. Instead, you have to think holistically about ways to secure your Docker containers and harden your container environment at multiple levels. So security is not set it and forget it. It requires vigilance to keep your images and containers secure. If you don't know where to start, you could think about threat modeling. That it is a process where you can identify potential threats and helps prioritize possible mitigations. So you want to be thinking of security as a feature by asking yourself the right questions. So ask yourself regularly, do we have any security requirements that you need to be filling in? So what we really wanted you to take with you today is that security is everyone's responsibility. And you don't need to spend much time or invest in a big infrastructure to start making this part of your continuous delivery. So finally, let's remember to build with the bare minimum and from trusted sources, ship with control resources, and run with the right permissions.
So that's it. Thank you very much for listening to our talk. We hope you all learned something that you can take away with you today.